one term can open up this whole hidden history, like sub-electron. It sounds, well, pretty straightforward, right? Less than an electron.
You'd think so.
But the story behind it, where it came from and what it means now, it's actually kind of mind-blowing.
It really is. And that's exactly what we're going to explore today. Our plan is to really unpack subelectron, trace it from this, let's say, controversial idea in physics way back when,
Right,
to what it represents now in like super advanced technology.
and we're digging into the specific topic because you, our listener, pointed us to the source material, these excerpts from Sub-Electron, History and Modern Application.
Yeah, thanks for that suggestion.
Honestly, when I first saw the title, I thought, okay, that's niche. But digging in, wow, it's a whole journey through scientific arguments, ingenuity. I'm actually really excited to unpack this with you.
Me too. So let's set the scene. We need to go back early 20th century. Physics was really grappling with the nature of electricity then. You had Robert Millikan doing his, famous oil drop experiment.
Yes, the oil drops. Classic stuff.
Exactly. And his work strongly suggested that electric charge wasn't some continuous fluid, but it came in these little packets, discrete units.
The multiples of a fundamental charge, right. The electrons charge you.
That's the one. So the picture seemed clear. Electrons are fundamental, charge is quantized. Simple.
Seems simple. But then enter Felix Ehrenhaft. His experiments sounded different.
Very different. Ehrenhaft was looking at these really tiny particles, incredibly small, and he started reporting measurements that, well, they didn't fit Millikan's neat picture.
How so?
He claimed he was seeing charges smaller than E.
Right, smaller. That must have really thrown a wrench in the works, yeah.
Oh, absolutely.
I mean, if he is the fundamental indivisible unit, how do you get less than that? It's like back then finding half an atom or something.
That's a great analogy. And that's exactly why Ehrenhaft's results were so provocative and, deeply controversial. He even coined a term for them, subelectrons.
Subelectrons. Okay.
These hypothetical particles, he said, carried fractional charges. He reported values like 1/2 E, sometimes 1/10. He even mentioned 1,000th of an electron's charge at points.
1,000th, wow. So you've got Millikan over here with his neat whole numbers, 1E, 2E, 3E, and Ehrenhaft pops up saying, hold on, folks, I'm seeing fractions. That must have sparked some intense debates.
Intense is putting it mildly. It was a direct clash. It basically challenged the core understanding of atoms and charge that was just starting to solidify.
If he was right, that changes everything. The whole picture of matter would be wrong, or at least incomplete.
Exactly. Fundamentally incomplete, perhaps.
But as the source material points out, Millikan's view eventually won out. The scientific community largely accepted his quantization of charge. Why was that?
Well, there were a few things. Millikan's experiments, they were seen as very carefully done, very rigorous. And crucially, other scientists could replicate his results, get that same value for E.
Reproducibility. Key in science.
Always. Plus, people started raising questions about Ehrenhaft's methods. Were there experimental errors? Could his observations be explained in other ways without needing fractional charges?
Okay. So maybe impurities or interactions he hadn't accounted for.
Things like that. While Ehrenhaft was definitely a respected physicist, the bulk of the evidence just kept pointing towards Millikan's quantized charge.
Yeah.
But the important thing here, and the source notes this, is that the debate itself was valuable.
Even though his idea wasn't confirmed.
Yes, because it forced everyone to be even more rigorous, to really scrutinize their assumptions and experimental techniques. It's a good example of how science progresses, by challenging the status quo, even if the challenge doesn't ultimately stand up.
Okay. So Ehrenhaft's free-floating subelectrons, these particles with fractional charge, they weren't really accepted. Is that the end of the subelectron story then?
Not quite. That's what's so interesting. The term didn't just vanish. While his original idea about free fractional particles faded, the term subelectron itself, it kind of got recycled. It evolved.
Okay. So it reappears later, but meaning something different.
Exactly. Fast forward to today in modern science and engineering. When people talk about subelectron now, especially with advanced detectors, they mean something totally different.
Not particles.
Not particles with fractional charge, no. It's about technological capability. It refers to achieving incredibly low levels of electronic noise in measurements, or extremely high resolution.
Oh, okay. Hold on. So subelectron noise doesn't mean noise caused by fractional charges.
No, absolutely not. That's the key distinction. It means the background static, the inherent electronic fuzziness in the detector, is so low.
So low that.
So low that the instrument can reliably detect signals that are actually weaker than the signal you'd typically get from a single electron interaction.
Yeah.
Or it can measure the number of electrons collected with an uncertainty that's less than 1 electron.
Wow. Okay, that's incredibly precise. It's like being able to hear not just a pin drop, but maybe the sound of the air moving around the pin as it drops.
That's a pretty good way to put it. Think ultimate sensitivity.
So why do we need that? Where is that level of fine-grained measurement actually necessary?
Oh, in a lot of cutting-edge areas. Astronomy and astrophysics are huge ones.
Right, looking at faint objects.
Extremely faint. Think about trying to detect the light from an exoplanet orbiting a distant star, or seeing the very first galaxies forming billions of years ago.
The signals would be incredibly weak after traveling all that way.
Exactly. Those faint photons might only generate a tiny handful of electrons in your detector's pixel.
Yeah.
You need subelectron noise performance to even register those signals reliably, to pull them out from the background.
Makes sense. What else? Any other fields?
Particle physics, definitely. Especially in searches for things like dark matter.
How so?
Well, many dark matter models predict that if a dark matter particle does interact with normal matter, it might only produce a very, very small signal. Maybe just 1 or 2 ionization electrons in a large detector.
So you need to be absolutely sure that the 1 or 2 electrons you think you saw were real and not just random noise.
Precisely. Distinguishing those incredibly rare, faint events from any background noise is paramount. Sub-electron sensitivity is critical there.
Okay, astronomy, particle physics. The source also mentioned advanced imaging. How does it fit in there?
Right, advanced imaging systems, especially those using specific types of sensors, like CCDs, charge-coupled devices.
Like in digital cameras.
Sort of the ancestors, yeah. But even more so with really specialized versions like Skipper-CCDs or things called Susuro devices and some advanced CMOS sensors too. These are designed specifically to minimize noise.
Okay.
Achieving subelectron noise lets them create incredibly detailed images even in extremely low light, or measure very subtle variations in brightness.
The source specifically called out Skipper-CCDs. How do they pull off this low noise trick? What's special about them?
Yeah, Skipper-CCDs use a clever technique, often called non-destructive readout, or NDR.
It's not destructive, meaning you don't use up the signal when you read it.
Exactly. So imagine a pixel collects, say, 3 electrons from incoming light. A normal CCD reads that charge once, measures it, and the charge is gone.
Okay.
With NDR, a Skipper-CCD can measure the charge in that same pixel multiple times, hundreds, even thousands of times, without actually removing the electrons.
How does measuring it lots of times help?
Because the electronic noise is largely random each time you measure.
Yeah.
But the actual signal, those 3 electrons, stays the same. So if you average all those multiple measurements.
The random noise starts to average out towards 0, but the real signal gets reinforced.
You got it. You effectively cancel out the noise, allowing you to determine the true number of electrons with incredible precision. Maybe say it's 3 plus or minus, say, 0.1 electrons. That's sub-electron precision on the count.
That's really neat. It's like taking lots of slightly blurry photos of something dim and stacking them in software to get one sharp image.
That's a perfect analogy. Same principle, applied electronically. Now, there's one more bit we should touch on from the source. Quarks.
Right. I saw that too. Quarks do have fractional charges, don't they? Like plus 2/3 E or minus 1/3 E.
They do. Up quarks are plus 23, down quarks are minus 13. Definitely fractional.
So, are those the modern subelectrons then? Did Ehrenhaft just predict quarks way ahead of time, sort of?
That's a really interesting question, and it makes sense to ask it. But generally, no. In particle physics, the term subelectron isn't really used to describe quarks.
Why not? They have fractional charge.
The main reason is confinement. Quarks are never, ever observed freely in isolation. They're always bound together inside other particles, like protons and neutrons. Those are called hadrons.
Okay, so we only see combinations of quarks, and those combinations always add up to whole number charges, like plus 1m for a proton, or 0 for a neutron, or 0.
Exactly. So while the individual quark charges are fractional, we don't encounter free particles whizzing around with plus 23e charge. Ehrenhaft subelectrons were imagined as fundamental, free particles with fractional charge. Quarks aren't like that.
Got it. So it's about confinement, and also just how the terminology developed in the field. Quarks are quarks, not subelectrons.
Pretty much. It's a context thing.
Okay, so let's recap then. This term subelectron, It's got this really interesting split personality.
It does.
It started out way back as this controversial idea about actual physical particles existing freely with charges smaller than in electrons.
Right. An idea driven by Ehrenhaft's experiments, which ultimately wasn't borne out by the broader evidence for those specific free particles.
But the term didn't die. It got repurposed. And now, in modern tech.
Now, it overwhelmingly refers to this amazing capability of our instruments, achieving noise levels so low that we can effectively work below the level of a single electron's typical signal, or measure electron numbers with fractional precision. It's about sensitivity, not fractional particles.
It's quite a transformation for one word, isn't it? From a fundamental physics debate about the nature of charge itself to being a benchmark for the performance of cutting-edge telescopes looking for exoplanets or detectors hunting for dark matter.
It really shows how science moves, how ideas get tested, debated, sometimes discarded, sometimes transformed, and how technology pushes everything forward, even our language.
Absolutely. It's a testament to that whole process of inquiry, challenging assumptions, building better tools.
Yeah, and refining our picture of reality along the way.
So for you, our listener, maybe chew on this. That relentless push to see fainter things, to measure more precisely, whether it was Ehrenhaft and Millikan arguing about the basic unit of charge, or today's scientists trying to catch whispers from the early universe, that drive is what fuels so much innovation.
It really is.
Think about where else this kind of ultra-sensitivity, this sub-electron capability might lead. We talked about space and particles, but what about, say, medical imaging, seeing disease processes at an earlier, fainter stage?
Or environmental monitoring, detecting minute traces of pollutants.
Or maybe even fundamental components for quantum computing, where controlling single electrons is key. The ability to perceive and measure things that were previously lost in the noise could open doors we haven't even imagined yet.